right? A linear differential equation of nth order. Again, the kinds that we will investigate would be the following: a naught nth derivative of y with respect to x, a1 n minus 1th derivative of y with respect to x, a2 n minus 2th derivative of y with respect to x, plus an y equal to 0, plus an y equal to 0. This is the differential equation that we are going to investigate next. Realistically, a0, a1, a2, an can be functions of x and y, but at this level we would look into a0, a1, a2, an being constants, being fixed constants. a0, a1, a2, an being fixed constants. We'll look at the possibility of solving this differential equation for a0, a1, a2, an being constants. But even before I venture more into this, let me introduce some terminology primarily with the objective of bringing about compactness in our representation. First of all, let me call ddx. ddx is an operator. Realize that when it operates on a function of x, it will give me another function of x. When it operates on y, it will give me some function of x, right? So ddx is like an operator, and we refer to this operator as d. D is this operator ddx, henceforth. So if I have to write ddx of y, I'll say d of y. D of y means d when it operates on y. Let's say y is a function of x, then d when it operates on y will give an output which itself will be a function of x, right? So let me call this operator as ddx. It can operate on y to give me a certain output which itself would be a function of x. d2 dx2 as d squared. I'll call it d squared. What this means is d dy. That means, right, the first derivative of y with respect to x, and the d acting again on the first derivative, giving me the second derivative, right? d of y essentially. So when this dy produces an output which is a function which when acted upon by d gives me the second derivative of y with respect to x. So d squared is like an operator in which you got to differentiate 2 times with respect to x. Going this way, I'll call as the nth derivative, right? Now, when I say d squared, or rather d plus alpha into y, if d is an operator, d plus alpha is also an operator. Basically, d can be written as d dx plus alpha. Alpha is a fixed number, is a certain constant. This would give me like a dy dx plus alpha y, which would give me like a dy dx plus alpha y. So when d plus alpha operates on y, it gives me d of y plus alpha into y. It gives me d of y, right? That is d acting on y plus alpha y. D acting on y plus alpha y. So d plus alpha acting on y is like a d acting on y plus alpha y. That's what this means. When I say d plus alpha acting on a function, that function is d plus beta acting on y, right? D plus beta can act on y will give me a certain function on which the operator d plus alpha can act, right? This would mean d plus alpha, d acting on y plus beta acting on beta into y plus beta into y, right? Now, which would be like d acting on dy first. So d acting on dy would give me d squared by second derivative of y with respect to x. Then d acting on beta y plus alpha into d acting on y plus alpha beta into y plus alpha beta into y. Right. Now alpha into d acting on y, realize that d of a constant into y is c into d acting on y, isn't it? So then alpha is a constant, alpha into d acting on y, d acting on y would mean d acting on alpha y, this would mean d acting on alpha y. So I could replace this by d acting on alpha y right? This would mean the other thing is ddx of y1 plus y2, where y1 and y2 are two functions of x. ddx of y1 plus y2, where y1 and y2 are two other functions of x, is like ddx of y1 plus ddx of y2, ddx of y1 plus ddx of y2, right? Which is like d acting on y1 plus d acting on y2. And what was the left hand side? The left hand side was d acting on y1 plus y2. So d acting on y1 plus y2 is like d acting on y1 plus d acting on y2, right? So now d acting on y1 plus d acting on y2 would be d acting on y1 plus y2. D squared acting on y plus d acting on alpha plus beta into y, right? Alpha plus beta into y, plus alpha beta y plus alpha beta y. Clear? Can I write this as an operator d squared? After all, realize that this alpha plus beta can come out. This alpha plus beta can come out. D of c into y would be c into d of y. So this alpha beta plus beta can come out. This way. Could I write this as d squared plus alpha plus beta into d plus alpha beta? This is an operator, this acting on y. Could I write this expression this way? Realize that this would give me d squared acting on y plus alpha beta into d acting on y plus alpha beta y, which is what this expression is, right? Now what this brings to us is the following. d plus alpha acting on d plus beta into y. D plus beta acting on y. This is an operator which is acting on this function. What is this function? This function is produced and d plus beta acts on y. This is like d squared plus alpha plus beta into d plus alpha beta acting on y. That means even though d is an operator, I can carry out the regular algebraic manipulations, right? It's as if I had a x plus alpha into x plus beta. I would write as x square plus x into alpha plus beta plus alpha beta, right? So you could carry out those kinds of manipulation and it's all validated. Do you realize that? So it's as if I had like a g minus 1 operating on d plus 2 y. D plus 2 y is a function. So d minus 1 operating on this is as if the operator d squared plus d minus 2 x and y. See, it's as if, it's as if I'm multiplying these two. The effect is as if I'm multiplying, right? The effect of these two operators acting on y, first this acts on y and then d plus alpha acts on the output of this. It's as if d squared plus alpha plus beta into d plus alpha beta acts on y. The effect is the same, implying what? Implying that I could carry out a manipulation of these operators. If I had a product of operators, I can multiply them. I could multiply them in exactly the same manner I multiply algebraic expressions, and it will all make sense, right? It will all make sense. Clear? The other thing which is to be noticed is that instead of this, if that, if whatever I have said is true, then this should be the same as d plus beta to d plus alpha acting on y. That means if you swap these two operators, that means make d plus alpha act on y and then make d plus beta act on the output of this operation. It's going to produce the same result, because what we have validated and authenticated is the legal multiplication, as if, right? So these operators will behave as if they were algebraic expressions. Their behavior is like algebraic expressions. It's not like it's a d squared and so on and so forth. It's as if they are algebraic expressions. Did you get me right? And these two could be interchanged. In fact, in general, if I had n number of operators, for example, g minus alpha 1, g minus alpha 2, d minus alpha n, g minus alpha 3, d minus alpha n minus 1, g minus alpha n, and this acting on y, it's as if first d minus alpha n acts on y, and then d minus alpha n minus 1 acts on the output produced by this, and then the next operator acts on the output of this, and so on and so forth. Now that we have established the multiplication legal, right, just like algebraic expressions, we could reduce this to one single operator. We could reduce this product of operators to one single operator, which would be, as mentally imagining g to be like something like an x or a variable t kind of a thing, right? So if you imagine d to be a variable t and then carried out this operation, product of operators, then this would turn out to be like a d to power n minus sum of the roots alpha 1 plus alpha 2 plus alpha n dn minus 1 plus sum of the product taken 2 at a time, alpha 1 alpha 2 did n minus 2th derivative, and then minus sum of the product taken 3 at a time, n minus third derivative and plus so on and so forth up to minus 1 to power n alpha n. This product of operators could be reduced as one single operator, which is this, and all of this can act on y. All of this can act on y, which means it's going to be d to power n acting on y, that means the nth derivative of y, then minus alpha 1 plus alpha 2 plus alpha n into n minus 1th derivative acting on y, then sum of the product taken 2 at a time, then the n minus 2th derivative acting on y, and so on and so forth, right? So this becomes like a single operator, and you may want to call this entire thing as, let's say, some function of d, an operator function, This entire thing is a function of d, so you can call it an operator function acting on y, right? So you can loosely speaking, you can call it an operator polynomial. You can call it an operator polynomial equivalently. It's not a polynomial, it's an operator which can, it's not a number really, it's an operator which can act on something, but it follows those rules of algebraic multiplication. Okay. So in general, if I had something like this, a naught nth derivative of y with respect to x plus a1 n minus 1th derivative of y with respect to x, a2 n minus 2th derivative of y with respect to x, an y equal to 0. This was a differential equation of order n and degree 1 This I could write as, in operator notation, I could write this as a naught dn a1 n minus 1 a2 n minus 2th derivative plus an. This is an operator. This is the operator function fd. And all of this acts on y to give me 0. Right? Where a naught, a1, a2 for this equation I would treat as constants. So we write this as some fd acting on y. Fd acting on y equal to 0 is the differential equation to be solved. Fd acting on y equal to 0 is the differential equation that we want to solve here. Alright. So the other thing that you may want to check is, or you may have realized by now, if I can multiply vector operators, I can also factorize operators. For example, if I have like a d squared minus 5d plus 6 acting on y, then I have the leverage to factorize this also. I could write this as d minus 3, d minus 2 acting on y. I could write this, right? I could factorize this. So this is the differential equation whose solution we are seeking, where the supporting coefficients are all constants independent of x and y, right? Now, few properties of this polynomial operator, few basic properties of this polynomial operator. When this operator, again this follows straight from properties of derivatives, because you know these are only derivatives of different orders, nth order, n minus 1th order, and so on and so forth. So it will inherit some of the properties of basic differentiation, right? So fd, if it's an operator and it acts on some constant times y, if it acts on some constant c times y, then this C can come out. Then this C can come out of this operator. So this will be C times FD acting on Y. This would be C times FD acting on Y, right? Because the C can come out of each of these derivatives. See, replace this Y by CY, then the C will come along with this. So it comes out of the operator sign. It can come out of the operator sign. A constant C can scoop out of the operator sign. Also, FD acting on some y1 plus y2. y1 and y2 are two other functions on which this operator function is acting. This operator function is acting. This would be FD acting on y1 plus FD acting on y2. And not just y1, y2, any number of functions. I mean, if I had FD acting on y1 plus y2 plus yn, then that's going to be FD acting on y1 plus FD acting on y2 plus FD acting on yn. Right? Now, if we have v some function of x, v as some function of x, then d acting on e power alpha x v, d acting on e power alpha x v, where v is some function of x, is e power alpha x into d plus alpha acting on v. I repeat, and I'll show you how that comes. This is a property. D acting on, that means the operator d, which is ddx, operating on e power alpha x v, is like e power alpha x into d plus alpha acting on v, is like d plus alpha acting on v. Look, start with this. This is like the derivative of this into this plus derivative of this into this, right? So if you apply the product rule for differentiation, d e power alpha x, which would be some function, into v, plus e power alpha x into dv, d acting on v, derivative of first function into second function plus derivative of second function into first function, right? But what's d of e power alpha x? Alpha e power alpha x v plus e power alpha x dv. You can take e power alpha x common. So if you took e power alpha x common and just realign terms, you will have d acting on v plus alpha into v, d acting on v plus alpha v, right? Which is like e to power alpha x d plus alpha acting on v, d plus alpha acting on v, isn't it? D acting on v plus alpha into v is like d plus alpha acting on v. So d of e power alpha x v is like e power alpha x into d plus alpha acting on v. This is a property of the operator ddx. It's a property of the operator ddx. Clear? Now, all of you understand this, right? Nobody is confused about anything that I have said here. Now when I say d squared e power alpha x v, when I say this, d squared e power alpha x v, alright, this is like d acting on, d squared is like d acting on d of this, right? But from this property we get this is like d into e power alpha x into d plus alpha acting on v. Yes or no? Now reread this property. D acting on e power alpha x into some function is e power alpha x into d plus alpha acting on that function, right? Now in this operation, this is the new v, this is the new v. So d acting on e power alpha x into this after all will be some function of x. D plus alpha when it acts on v would be some v prime, would be some function of x, right? So now if I deploy this property, d acting on e power alpha x into some function, this is some function, would be e power alpha x into d plus alpha acting on this function d plus alpha. তোর চোখে কিছু হয়েছে জয় বাংলা? d plus alpha acting on this কিছু হয়নি, জ্বালা করছে আর চোখ করে কি? Do you realize this? I've used this property. D acting on e power alpha x into some function, d plus alpha acting on v is some function, right? Would be e power alpha x into d plus alpha acting on this function, which is what I wrote here, right? Which is like saying e power alpha x d plus alpha whole square, right? Now I can do this because this operator is like the operator d squared plus 2 alpha d plus alpha squared. We have established that algebraic relationship acting on v, right? Which means d squared e power alpha x v is e power alpha x d plus alpha whole square acting on v. Similarly, you're going to get d cubed e power alpha x acting on v would be like e power alpha x d plus alpha whole cubed acting on v. Going this way, you're going to get nth derivative of e power alpha x v is like e power alpha x d plus alpha whole power n acting on v. This is the property that I was trying to bring across to you, where v is some function of x. This is the property to be noted. In fact, the bigger property that we were eyeing by means of this was the following. Can I wipe this off? Where d is ddx and fd is that polynomial operator that I defined, a naught d to the power n plus a1 d to the power n minus 1 and so on and so forth. A generalization of this property is fd. Fd is what? A naught d to the power n plus a1 d to the power n minus 1 a2 d to the power n minus 2 plus an. That's fd. All right. This acting on e power alpha x v is going to be actually e power alpha x f of d plus alpha acting on v. In that fd, replace d by d plus alpha. This is the generalized property. Fd acting on e power alpha x v is like e power alpha x into f of d plus alpha acting on v, where fd we saw was